So in this next unit, we're going to be dealing more with kind of the structure and function of atoms. So one of the places that I'd like to start is by going back and summarizing Rutherford's model of the atom. So why don't you pause and see if you can get this all on your own, and if not, go back, look at your notes, and kind of try to figure it out. So what Rutherford said, or what Rutherford discovered, was the nucleus. So the center of the atom had this positive charged area that was much smaller than the rest of the atom. And so here's the rest of my atom. And then the electrons, he wasn't quite sure what to do with those. He just had them kind of around the atom, distributed around the atom. But the key was this central area, the nucleus, that had a positive charge. So hopefully the question that springs immediately to your mind when you look at this again is, well, electrons have a negative charge, the nucleus has a large positive charge, why don't electrons just collapse into the nucleus? And that's actually a really good question, and it took scientists a really long time to figure out why that didn't happen. And the answer, actually, interestingly, did not come from the study of matter, it came from the study of light. So we're going to talk a little bit about light basics. Electromagnetic radiation is a form of energy that has wave-like behavior as it travels through space. I'm going to dark that out a little bit. Okay, so here's a wave that's traveling towards the beach. And actually, a lot of waves work a lot like waves at the beach. Okay, so the waves progress towards the beach, and the distance from one wave, from the top of one wave to the top of another wave, we call these the crests, is the wavelength of that wave. Okay? And that has the Greek letter lambda. All right? So that's just the distance between corresponding points in a wave. Now, interestingly, all waves of electromagnetic radiation travel at the same speed. So imagine this waves on the beach are really just this force that's moving towards the beach. So that force is traveling, okay? And electromagnetic radiation also travels through space, through air, through a vacuum, all roughly at the same speed. Okay, the speed of light has, since it's a constant, we give it a value, c, which is 3.00 times 10 to the 8th meters per second. And if you're wondering, yes, this is where E equals mc squared, that c is the same. Okay, now another piece of information that'll be helpful for us is the frequency, which is the Greek letter nu, which looks like kind of a curved V. And frequency is the number of waves that pass a point in a given time. Okay, so this is really like waves over time. Okay, which means that the units are going to be slightly strange here. Okay, waves, this is just a count, so there's really no unit on top. Okay, but there is a unit on bottom. That's seconds. Okay, so the unit of frequency is 1/seconds, or s to the minus 1, or this is also known as a hertz, which has the symbol Hz. Okay, and so let's say that you're sitting right on top of this pier here, and you're kind of watching this point. Okay, here's my eye, I'm watching this point. The frequency is really just counting the number of crests that pass by me in a given amount of time. Okay? So all electromagnetic radiation combine to form the electromagnetic spectrum. And you can see that visible light is really just a very, very small section of the full electromagnetic spectrum. Okay? You'll notice that this goes down to 10 to the minus 2 nanometers. Remember, nanometers are 10 to the minus 9 meters, all the way up to 10 to the 4th meters, which is like 10 kilometers. So there's a huge range of wavelengths. And also, you can tell that there's some sort of relationship between wavelength and frequency. So as wavelength increases, so we're getting bigger this way, right? The frequency actually gets smaller going that way. So that should tell you that these two things are inversely proportional, all right? So we know that wavelength is inversely proportional to frequency, all right? And so I can say that wavelength is proportional to 1 over the frequency. That's really, those two statements are the same. And in order to make a proportionality into an equality, I can add a constant. So the first thing I'm going to do is I'm going to multiply both sides by the wavelength. And I'm going to say that the wavelength times the frequency equals some constant. So wavelength times frequency equals a constant. I just need a little bit more room here. Some constant, and we'll call that K for a moment. Now let's look at the units. All right. What are the units of frequency? That's right. They're 1 over seconds. And the unit of wavelength is a meter, so meter over 1, which means that the unit of this constant is meter per second. And that sounds like a speed, right? So this K happens to always be true. It is the speed of light. So the equation then becomes the frequency times the wavelength equals the speed of light. Okay? So that's kind of important stuff to keep in mind. Now, let's get into the nuts and bolts. That's like a background on light. Nuts and bolts of how things were discovered. Okay? A big thing here is the photoelectric effect. All right? And I want to show you a little video right now on the photoelectric effect.
When light strikes a metal surface, electrons may be ejected. This process is called the photoelectric effect. Each metal has a characteristic energy level. If the incoming light is below this level, no electrons will be ejected. For example, this red light is not sufficiently energetic to eject electrons from cesium metal. Yellow light is also not energetic enough to eject electrons. Green light is energetic enough to eject electrons and current flows.
Okay, so here's just that diagram again. All right, you have like a battery plugged into two metal plates, and you know that the two metal plates on their own, if they're far enough apart, won't conduct electricity, right? You need to have a full completed circuit. All right, but what scientists found was that when they shone light on one of the plates, that light was able to knock off some electrons, and then the electrons could go from the negative plate, where electrons would be, to the positive plate, where there were no electrons. Okay, so that's kind of the photoelectric effect. And the interesting thing about the photoelectric effect, as they mentioned in the video, was that light needed to have a minimum wavelength in order to eject an electron. All right, so that's photoelectric effect. That's the kind of important stuff there. All right, then came a guy named Max Planck. and he studied energy releases by hot metals. And he finds that energy is released in small packets of energy. He calls quanta. And there's another really good video that I wanted to show you on this too.
In 1900, Max Planck theorized that a hot object does not emit electromagnetic energy continuously. Instead, Planck suggested that objects actually emit energy in small, specific amounts, or quanta. Energy, he said, was quantized. In other words, the energy being emitted has only certain values, almost as though the energy is a packet. Some wavelengths of light carry only a little energy at a time. Others carry more. But the energy is always quantized. It is always in terms of the packet. The smallest possible amount, one packet or quantum, is defined as the minimum quantity of energy that can be gained or lost by an atom. Quantization becomes important when light or another form of energy interacts with an atom. Sometimes the incoming energy is enough to make something happen, other times it is not. Think of rolling a ball out of a pit. The energy must be enough to get the ball out of the pit all at once, or the ball will simply roll back to the bottom. Even if the energy of multiple rolls would add up to enough energy, the ball will not have been able to get out of the pit because the energy of each hit in itself was not sufficient. With enough energy in a single hit, the ball escapes from the pit. Similarly, if the packet of energy is not large enough, the atom is unaffected, despite the fact that the packets of energy keep coming. If the packet of energy is sufficiently large, however, the atom is affected. An electron, for instance, may become excited.
Okay, so there's a lot of good stuff in there. I really like the analogy of the golfer, right? So Planck finds that the energy is released in small packets that he calls quanta, and he uses this to explain why light needed a minimum wavelength in order to eject electrons. So he was actually able to relate the energy of light to the frequency of light. And he said that they're actually directly proportional if you add a constant. And so this is energy. This is going to be, the units are going to be joules. Okay, this is Planck's constant. Planck's constant. And this has a value of 6.626 times 10 to the minus 34 joules times seconds. And this is going to be the frequency of the light. Okay, remember, I'm giving you all these equations on the equation sheet. I'll give you this constant on the equation sheet. You just have to be able to identify them and know what they mean. Okay, so that's sort of the first bit of information that we need to keep in mind, okay? That light, the energy of light is quantized. Okay, a little bit later, there was this pretty smart guy who taught at Princeton for a little while. His name went by the name Albert Einstein. Okay, and he proposed that light could behave as a wave and a particle. Okay, a wave and a particle. He called these particles photons. Now, the interesting thing about photons is that they have zero mass. So, technically speaking, they don't exist, okay? But they do, but they don't. All this stuff is going to get very, very weird, all right? You just have to kind of bear with us, and I will say that even now, scientists do not understand fully what goes on at these small levels, okay? So we're doing our best. We'll get there one day. And he said that each photon carries a quantum of energy, which he described using the equation E equals h nu. Okay, so E equals h times the frequency. And the way that he used this to explain the photoelectric effect was that he said matter can absorb photons only in whole numbers. All right? So for each electron, there's a minimum energy needed to, quote, knock it loose from the atom. The electron must be struck by one photon with the minimum energy needed to knock it loose. If the photon has less than the minimum energy, the electron stays in the atom. Okay? So this was all kind of theoretical, but there was an experiment that is really important. All right? When electricity, which is a form of energy that is actually not like a wave, is passed through a sample of gas. So gas is really just lots of electrons with lots of free space in between the electrons. The electrons gain potential energy and move to an excited state. Okay, so the lowest energy state, the most stable of an atom, is called the ground state. So I always like to draw the analogy of a textbook. Okay, so here's me standing at the front of the class. You'll be amazed by my artistic ability. And I put a book on top of a table. Okay, now that book actually is not real happy. It doesn't want to be on top of the table. What would happen if I, just kind of slid my hand sideways and knocked the book off the table? Well, it would fall to the ground. Okay, so when the book is on the ground, it is in its lowest energy state. Okay, we call that the ground state. And things tend to prefer to be in their lowest energy state. So this lowest energy state, the ground state, is the most stable state. When electrons move from an excited state to a lower energy state, it emits energy. When it moves from a lower energy state to an excited state, it gains energy. Okay, so these are all important things to keep in mind. All right, so let me kind of go through the setup of, or what kind of diagramming this a little bit, right? So here's my ground state. Okay, here's my excited state. Oops. And when an electron from an excited state moves to a lower energy state, it emits energy. And energy has to be conserved, kind of like mass, okay? So since we're since we're moving from a higher energy state to a lower energy state, we have to release some energy. And the way that the energy is released is in a photon, okay? So the energy of this photon would be equal to the energy of this level minus the energy of this level, or, as we already know, E equals h times nu, all right? So what scientists did is they filled a tube with hydrogen, and then they excited all the electrons and looked at the light through a prism, okay? So what they were expecting to see is like a rainbow, basically, okay? They were expecting to see that there were lots and lots of different transitions allowed, or lots of different transitions possible, okay? And if that's the case, then you should get photons with a bunch of different energies, meaning a bunch of different frequencies, meaning a bunch of different wavelengths, meaning a bunch of different colors or lines on the electromagnetic spectrum, okay? So they were expecting to see kind of a rainbow. But that's actually not what they saw. And this was really interesting, all right? So here's our tube filled with hydrogen gas, and you send electricity through it, and it starts emitting this kind of purplish light. And you pass that purplish light through a prism, and the prism bends the light so that you can project it onto a screen. And what happens with hydrogen is you get these 4 bands. This fifth one is kind of barely visible. We'll do this, and I'll ask you to try to find that one. But yeah, this one's very hard to see. So, by the way, this might be important. This is in the textbook. Wink, wink, nudge, nudge. This figure might be helpful to you. Oh, I don't know, sometime when you might have to write a formal lab report. I don't know, maybe something wink, wink, nudge, nudge. Okay, so that's the experiment. Okay, this is the hydrogen emission spectrum. Okay, it doesn't, in fact, have a continuous rainbow. There are these 5 discrete bands. Okay? And what that tells us is that instead of being able to get this whole thing, we only get certain transitions allowed. So the ones that are above are these ones, these Balmer series, and these are visible. Okay? So what's going on here? Well, this leads people to the conclusion that only certain energy levels are allowed, right? Because if I go back a couple slides, and I take a look at this and I say, okay, so anytime that there's a transition, I could release a photon that would have a certain frequency, okay? And so the fact that I only get certain bands means that there are only certain transitions allowed, certain energy levels allowed. Okay? So Niels Bohr took this and theorized about how the electrons are arranged about the nucleus. Not in a nucleus, but about the nucleus. So what he said was electrons orbit the nucleus in a circular path. Okay? This model is also called the planetary model because in this model, electrons orbit the nucleus kind of like planets orbit the sun. Okay? The orbit is separated from the nucleus by empty space. So this is sort of, I'm going to put an asterisk on this, okay? So Niels Bohr couldn't explain why there were only certain energy levels allowed, but he does take it into account in his model. He says the orbit is separated from the nucleus by empty space, things aren't allowed there. He doesn't know why, but he does explain, okay? It's part of the model. So the electrons, or atoms, are in the lowest energy state when the electron orbit is closest to the nucleus. So just like the textbook on the floor, okay, that's the lowest energy state. An electron that's closest to the nucleus is going to be in its lowest energy state, the most stable state. Okay? So if a photon, so here's my photon here, it comes in and it hits the electron, this electron that is in the lowest energy state. So here's one allowed orbit, E1. And this is the lowest energy state. This would be the ground state, right? So a photon comes in and it hits this, this electron, and the electron goes up to E2. Okay? So we call this process absorption. Now, the photon that comes in has to have this energy. Okay? It can't take the electron to like here. Okay? It has to take it up to here. But electrons, kind of like, you know, me holding the textbook in the air, electrons don't want to stay in an excited state. They want to be in the ground state. So what's going to happen is, once they move up to this excited state, they're going to what's called relax back to the ground state. And when they do that, because we have conservation of energy, they have to emit a photon. And that's that would be the difference in the two energy levels. And that process is called emission. Okay? So if I look at the allowed transitions, okay, here are a bunch of the, here are a couple energy levels from hydrogen, all right? And we already said that the Balmer series are the visible ones. So these ones are the ones that are kind of really important to us. One important feature here is they don't actually relax all the way to the ground state. They relax to the second energy level, and then from there they can relax again to the ground state. But that relaxation would produce infrared light, so we don't see it. Okay. Yeah. So this explains how this kind of relates this process of absorption and emission with energy levels. Okay, so each of these would correspond with one of the lines in the hydrogen emission spectrum. Back. Okay, each of these lines would correspond with one of these transitions from a higher energy level to the second energy level. Okay, so that's the Bohr model. And it's important to know how the Bohr model explains the hydrogen emission spectrum, but we're going to talk about some problems with the Bohr model and what was done to fix that next time.